But, all right, so now, I've actually never taught from these slides either. I stuck them in as trying to get some extra understanding. And last term I was doing this as we were, well, I guess I was making them as we went. We want a formal proof. Now, how do we prove that the language of this machine is the language we have in mind? So let me first give you a little warning about the notation here. All right? Here I have an L, and here I have an L, and those L's have very different meanings. All right? It's just like if I said f of x equals f, and this is mapping from a real number to a real number, right? Then this is a real number, and this is a real number, and this is a function, right? So that's kind of what we have here. If M is a DFA, then L might be the language of the DFA. And what's a language? It's a set of strings on which we say yes, right? So here, M is the DFA, L is the set of strings on which it says yes. So it's the language of the DFA. And what do we mean by L of M? Well, this L is a function that, given as input a DFA, or an NFA in this case, given an NFA, it tells me what the language is, right? And so what do we mean by prove this? What I mean is, I give you an M, here it is, there's a DFA. I give you an L, what it is all strings that contain 0, 1, 0, 1. And we want to prove that this machine accepts that language, right? Here's our M, there's our L. We want to prove that every string in here that's a yes, this machine says yes. Every string in here which is a no, this machine says no. All right? So now here I'm saying there exists an NFA. Well, we have it already, so it's not a problem, right? But we want to say that for every string, you give me any 0, 1 string, what the machine will say yes, if and only if the language says yes. Right? Everybody with me here? And what does that mean? Another way of writing it is we might write the string is accepted by the machine if and only if the string is in the language. Right? We use these various notations. Right? L of alpha equals yes or equals 1 if the string is in the language. Right? So we flip between those two notations. Are people kind of okay with that? Right? So I actually came up with 2 proofs of this. And actually I came up with 3 proofs. And then I thought, well, and I keep changing my mind, which one is the one that you guys should be going with? And the first 2 proofs I came with, I've decided neither of them are very good, and I eliminated one of them. And this first proof is one I think is better. All right? The second proof is the one I made them do last year. And so we're going to have a different proof this year. All right? This proof is going to be all about loop invariance. All right? It's all going to be about the names of the states. Right? You guys were asking, well, why do we care so much about the names of these states? And it's because we're going to use these names to prove that the program works. All right? And so this is just a caveat. I haven't made up the exam yet, but this is now my new proof of choice. All right? So the point is that we want to give the states. I mean, why do I use loop invariance? Right? When I start teaching 3101, and the first day I say, you know, if you're standing on a subway talking to somebody about your algorithm, you need a language in which to talk about it where you know that it works. Right? If I talk code, I don't know it works. Right? So you're going to find that this proof here, you're now worried that we're going to have this proof. But the proof is going to be just what we did. Right? When we designed it, we almost designed it to make sure that it worked. right, by having these names and having this loop invariant. All right? And so now we're going to do the proof, and the proof is going to rely on these names. All right? So what is the name supposed to do? The name is supposed to give you a set of strings for which there exists a path to that state. All right? And what does the DFA know when it's in the state? Well, if it's in the state, it knows that somehow I got to this state. So that means that there exists at least one path that comes there. Right? Now, what's the difference between this and the DFA world? In the deterministic world, every state followed one path. Right? So these sets needed to be disjoint. But they don't need to be disjoint anymore, because a string can have multiple paths, so it can land in multiple nodes. All right? Right? And now, what are we going to do? We're going to prove by induction on the length of the string that these names are correct. All right? So, here's how we're doing it. We have, what are we doing? We're saying what is our language of the machine? Right? By the definition of the machine, the language of the machine is the set of all strings that have a path to the accept state. Right? That's just definition. Right? That's the language of the machine. Right? So instead of focusing just on some states, we're not going to focus just on the accept states. We want to focus on each state. All right? So here I'm going to talk about what's the language of state 1. Right? Here are my states, 1, 2, 3, 4, 5. And we're calling column state 1, 2, 3, 4, 5. Right? And what is the language of this state? I'm going to say it's the set of all strings that have a path to this state. Right? And this is the set of all strings that have a path to this state. Right? Does that make sense? All right. And now we're going to do now this is kind of non-determinism again. We're going to guess names for these states. Right? And I'm going to guess, well, what strings can land here? Any string can land there. Right? Any string at all can land there. So I'm going to guess that the name of this state is any string. Right? And I put a prime here because it's just my guess. Right? And then, well, what strings can land here? Any string that ends in a 0. Right? What state can land here? Any string that ends in a 0, 1, 0, 1. Right? What can land here? Right? What can land here? Well, it's any string that contains 0, 1, 0, 1, because after we get here, we can spin again. Right? Does that make sense? So I'm believing that these describe each of the languages. Right? All right. So now, and as I said, this is what the machine knows when it's in one of those states. Right? If I'm in that state, it tells me which strings could have arrived here. And what do I know? Right? If I'm in this state, I know that I end in 0, 1, because the only states that can arrive there are the ones that end in 0, 1. Right? Now, here is just a little caveat that these no longer have to be disjoint because we have an NFA. Right? And that's one of the things that makes NFAs easier. We didn't have to make them disjoint. Right? All right, so what's our loop invariant? We need a loop invariant, right? We're at the top of the loop, and what's going to be true? What our loop invariant at time, loop invariant t is, I guess, is that for every state, these two sets, right? What is this set? This is the set of states, set of strings that actually has paths to it. And this is the set of states that we believe it has paths to it. It's the ones that have this name, right? And what we're saying is for each of the states, we were right for all strings that have length t, right? So that's the t statement, is that we were right for all strings of length t. Everybody got that? And we're going to do the proof by induction, right? This is our induction hypothesis, right? So how do we do it? By induction. We first prove the zero. Well, here, how do we prove zero and then we do the induction, right? How do you do induction? You assume this and you prove that. Now, what about the zero? What strings have length 0? Just the empty string, right? And where does the empty string belong? Well, where can you go the empty string get to? Only the first one, right? And look at, of these sets, which contain the empty string? Only the first one, right? So it's right for the empty string. Everybody buy that? All right. So here, how do we establish the loop invariant? We have to prove it's true for the empty string. Well, where's the empty string? Right? Here for state Q1, both Q1 here, both contain the empty string, right? And the others don't contain the empty string. Right? So we proved it's true for the empty string. Now we want to prove it by induction. Right? So we're assuming LT. So we have some string of length t. Right? For every string of length t, we assume that will be in the right states. Right? So here, we take an arbitrary string. We take some path. Right? And then we want to prove that it's true for one more step. Right? Well, if I have some path that I got here, and I take one more step, I get a 1, where am I going to go? I'm going to go there. Right? So that's kind of what we have to handle. We have to say, how are we going to prove this? Right? Well, I guess formally we have to say, give me an arbitrary string of length. Right? So here, let's say we consider state 5. We want to prove this for state 5. How do we prove it for state 5? Well, give me an arbitrary string of length t plus 1. Right? And I need to prove that, here I'm trying to prove that this equals this for all strings of length of length 5. Oh, no, all strings of length t. Right? So I take an arbitrary string of length t plus 1, and I have to prove that this equals this. And how do I do it? Well, we have to prove that this string is in this set if and only if this string has the name we said it should name. Right? This says there's a path to length 5 if and only if it has this name. So how do we do that? Well, this says, it has a path to length 5, to state 5. And this says, right, there it is. We say AC has a path of length to state 5. So here's our path of length 5. Right? I just made the last edge red because it was the C that we're reading. Right? So the alpha is reading this much, and the C is reading that much. Right? I don't know what we're supposed to do in a test. I haven't made up a test yet. Right now we're supposed to understand this. Yeah? Yep.
Let's say your input is 0, 1, 0, 1.
Yep. Then it contains it.
Okay. So something has to be...
We out of time? Excellent. We'll do this again next class. Any other questions before you run? Right, so on Monday we'll have a tutorial, and the first thing we'll do is take up the test, and then we'll do what other people want.